Okay, so the next thing we want to look at is arc length and sector area, and two formulas, a formula that we can use for each of those, which are a little bit special in that they have to be in radians. If you do these formulas in degrees, the answer is wrong. Like there's no saving it, right? It's just goofed up. But really the first one, the arc length formula, now we know the arc is just a section of the circumference of a circle, correct? Now, we tend to always think of an arc as being less than the full circle, but what we're going to work with in mathematically, the arc can be, you could do, I think we have a problem with like 10,000 revolutions, right? So the arc could be 10,000 times around. That's fine. It's math, we just don't tend to think of it that way. Now, the first formula here for arc length actually comes from, if you think back to how we defined radians, right? So this theta is our central angle, r is the radius, S is the arc length. We defined radian measure as the central angle was the arc length divided by the radius. Right? This is what we did with the little strings when we put the strings around the circle. If you remember that or not. Little wiry strings. It didn't work very well, but it, hopefully proved the point. Well, with this is just a nice formula. You can rearrange it and it gives you other information. So if we go ahead and multiply both sides by r, we get the arc length formula, which would be S equals r theta. So what this will do is if you know the central angle and you know the radius, you could find the length of the arc using this formula. You could find any of them. If you know two, you could find the other one. It's just a formula. You could rearrange it other ways as well. But because it comes from this radian formula here, and other reasons too, the big important thing here is that theta must be in radians. Okay? Must be. It won't work otherwise. It just won't work otherwise. So now the same idea, the same types of problems we're going to look at today, you may be able to do like a proportion of the circumference argument that may be used in geometry to answer the same types of questions. And they would be correct, but really try to kind of lean into the radian measure and get used to it. The more comfortable we can get with radian measure, the easier things are going to be going forward. I think this is a good kind of way to get started here. So our first example here, and we'll kind of see why degrees don't work here in this example, we'll take a second, is that we're told that we have find the length of the arc. So the length of an arc of a circle with radius 10 meters that subtends a central angle of 30 degrees. Okay, so like a lot of times our central angle might be measured in degrees, but it means we're going to have to convert that to use our new formula. So for this one, a picture's always nice. So with this, almost full circle. So we have this picture, and we have our central angle of 30 degrees. We're told our radius is 10 meters, and we're asked to find the arc length. Drawing a picture, as much as anything, is just a nice way to kind of organize your data, right? It's like a table, but it's a circle. It's just put your stuff on a diagram. You can refer back to it. So in this case, if we want to use this new arc length formula, which we do, the first thing we need to do is that we know theta is 30 degrees, but we know that we need to convert that to radians. We should know that conversion, right? 30 degrees is pi over 6 radians. So then S will be, we said, is r theta. So that's going to be 10 times pi over 6. So the arc length would be, reduces 5 pi over 3 meters. exactly. So 5 pi over 3 meters. Now, what we did, and we're not like, it's not physics. I don't make you write units on every step, but it is good to kind of keep an eye on the units. Okay. The advantage, the reason we have to use radians here, one of them is the radians we said don't really have a unit, correct? Because a radian is just a length divided by a length, so it has no unit. So when you do meters times no unit, you get meters for arc length, which it should be, right? It would be meters for arc length. Now, suppose that you did this incorrectly, and you just said theta was 30 degrees. And then now degrees is a unit, it has to be included. So if you did that, when you multiplied the radius in meters times some number of degrees, your unit for arc length would be a degree meter. I have no idea what a degree meter is. Right? If you can't go to Home Depot and ask for, a board of degree meters, it's probably not a unit that we want to work with. But no, it's not a unit. It would just be, it's kind of nonsensical. Now you could do like dimensional analysis after the fact, but don't. So remember, S equals R theta only works if you're in radian measure. Okay. So take a second here. There's a couple more examples on this page. Go ahead and try those. I would think you'll be able to get through the first one. The second one's a little trickier, and then we'll go from there. Okay, so for our second two examples, the first one, central angle theta in a circle of radius 4 meters is subtended by an arc of length 6 meters. So if we label here, we have 4 meters, 6 meters. Find the measure of theta in radians. Now, if you know, that's the definition of radians. Actually, one of our formulas we had was theta equals S over R. That's the answer. Now, maybe you forget that, but you remember S equals R theta. We know we're solving for theta, correct? I would always recommend you rearrange the formulas before you plug the numbers in. Especially if you take a lot of like chemistry or physics and you get these awful numbers that, there's so many awful numbers in physics, they start to use like obscure Greek letters to stand for them, and some Greek letters have to get used more than once. Like you don't want to type these, you don't want to do algebra with these numbers. You'd rather do letters. So here we get theta equals S over R. So that will give us 6 meters divided by 4 meters, right? Meters cancel, so theta is 3 over 2. What unit would that be in? Everything canceled. It would be in radians. That's what radians are all about. So since it doesn't have a pi with it, right, there was no pi, you might go ahead and throw radian after it just to kind of say, hey, this is an angle, it is measured in radians. Just kind of as a clarification. Not mandatory, but probably a good idea. Okay, this is a more interesting example, I think. A car's wheels are 28 inches in diameter. How far will the car travel if its wheels revolve 10,000 times without slipping? This is how your speedometer works, basically. It doesn't look at your wheels, it actually looks at one of your axles and it measures how many times it revolves. And at the factory, they set it based on the diameter of your stock wheels. So if anybody's ever put different sized wheels on a car, you notice it goofs your speedometer up, right? If you put smaller wheels on, it reads faster than you're actually going. If you put bigger wheels on, it reads slower than you're actually going. Like when I was in high school, these guys, they get these big trucks with jacked up tires and everything, and like they'd be on the interstate with traffic and it still said they were going 32 miles an hour because their tires were so big and their speedometer had never been reset. So, but anyways, let's see what we can do here. So in this case, we're not given a degree or a radian. We're actually given this revolve 10,000 times. For a lot of word problems, a revolution is how we're going to talk about things. That means the circle goes completely around, correct? So one revolution is the same as 2 pi radians is the same as 360 degrees, right? So we're going to need to use some dimensional analysis possibly to figure that out. Okay, so in this case here, we have our tire. It has a 14-inch radius. Don't make it 20. If you make it 28, it could cause you some issues. And then we know that theta is going to be 10,000 revolutions times 2 pi radians per revolution. So again, more dimensional analysis, correct? So I have that theta is 20,000 pi radians. Does that make sense? Now, why do I need radians? Well, because when the tire contacts the ground, correct? And it should be a point, if a point here goes completely around, it's traveled the circumference of the circle, correct? That's the arc length of a full circle. So that's why it has to say without slipping. When you spin your tires on the ice, obviously your speedometer says you're going really fast. You're not going anywhere. Right? It just thinks you are because your tires are spinning. So what we're going to do here is we have theta, we have r. So to find s, we just do r times theta. So 14 inches times 20,000 pi, which is a really large number. Now, I want the answer, though, in miles per hour. I think it said that on the paper, maybe. Like, we don't want to talk about how many inches you travel in an hour. Like, that would be very silly, right? So we have to do some dimensional analysis. How many inches are in a foot? You guys got that, right? 12 inches. So then the inches cancel. How many feet are in a mile? 5,280. That's a number we really should know. 5,280. I can't write it, but that's feet in a mile. So if we multiply this, we'll do 14 times 20,000 pi divided by 12 divided by 5280 should give us the final answer, which is 13.88 miles. Okay? Make sure you type that in at some point and it's working for you. Okay? Thank you. Then I'll post the video too.